Hey, John here. I've been messing around with this IMSAI 8080 front panel, trying to figure out why the data bit 5 and the M1 light don't work, and the ability to halt it doesn't work. And I took it apart last time, and today I am going to try to clean it up and put it back together again and see if anything changes. Somebody mentioned that they would recommend that I test or replace these capacitors in case there's a problem. And the kind of problems that you could have with an old capacitor like this, these are electrolytic, which means that they're filled with a liquid electrolyte inside of it. This is not unlike a battery, one that holds its charge a very short period of time. This is a 95,000 microfarad capacitor with a working voltage of 15 volts. So this can hold a heck of a lot of energy, okay? Now, if this thing had bad electrolyte in it, it could draw a lot of current through it, as I understand it, and heat up. And if it heats up, the electrolyte would then start to boil, release gases. This white dot here is like a little silicone plug. If this thing expanded, it would have to have a place for that gas to go. This plug would pop out, and if it expanded and heated up too quickly, that wouldn't even pop out. Soon enough, the whole thing would explode. That's not a good thing. Now, these days, about a decade ago, these days we're a little sensitive, because a decade ago there was a bunch of capacitors that were manufactured that had bad electrolyte in them, and they were notoriously used on a lot of PC motherboards, including big brands like Dell. And they had to replace all their motherboards because the capacitors all failed due to the bad electrolyte. Now, in that particular scenario, the one that I'm thinking of, what happened was the electrolyte had some conductivity in it, and the bad electrolyte caused there to be a DC leakage current that flowed through those capacitors, right? Which meant that there was a lot of current flow continuously through these capacitors, and it would heat up the electrolyte, okay? Which would then give off gas and expand, and it would blow the plugs or crack the case open or completely blow up, okay? Yeah, that could happen. These is 45 years old. Normally, if it would have blown up for reasons like that, it would have happened in the 1970s. I don't think that's going to happen to this capacitor, but what could happen is that, because remember it's liquid, it could still evaporate. Nothing's a perfect seal, all right? It's probably pretty good. May not be perfect. If that happens and the electrolyte all, vaporizes and leaks out of the thing and is gone, then what happens is the capacitance will go way down, and the AC resistance will also go up, which is actually the opposite of the DC resistance in terms of what you want, right? What would happen is that the value of this capacitor would go way down. It just would not be a very good capacitor and just cease to function. When that happens, they're not going to blow up. These things, if the electrolyte is manufactured properly, when it fails, what happens is they just become a very bad capacitor. And in this case, it's a filter capacitor, so they just wouldn't filter anymore, and we would see pulse DC current voltage going into our system rather than nice smooth DC. So how can you test such a thing, right? Well, what we really want to do is measure the amount of current that flows through this capacitor, the amount of DC current that flows through this capacitor, okay? So I got a power supply here, not a Cadillac or anything like that, but it has an adjustable output current knob here, an adjustable voltage knob here, and I wouldn't trust this meter as far as I could throw this thing, and I'm not exactly a baseball pitcher, so maybe my front yard, I don't know. Anyway, I'm not going to trust that amp meter. I'm going to trust my my trusty overpriced fluke meter instead, which will probably give me a very good reading, okay? So let's start with this. Let's look at the DC range and just measure the voltage on this capacitor. Make sure it's not currently charged. It says it's got 0.034 volts on there, and it's just wandering down to 0 right now. Is depending on how good of a conduction I have on these probes. If I shunt the probes together, it should say 0. Yeah, okay. and I go between the two terminals. There's a tiny amount of voltage on here. This little resistor here is called a bleeder, and the reason you put these on your circuits, this is a 220 ohm resistor, which means it'll draw some current, but it won't draw enough to heat itself up and burn up. If you put this across these two terminals and there's some voltage stored on here, it'll let that voltage go conduct through that resistor, and it will drain the charge out of it. So there's going to be some current. If you put this on here, we should slowly see this thing go down, down, down. Now it's going to go down at RMS speeds, which means it's it's an exponential decay, which means in theory it discharges slower and slower and slower. As the voltage is lower, the current is less, and so on. So this could take, in theory, forever to completely discharge. But 0.013 and so on. This is not charged. This is not going to be a problem. Okay. Not going to hurt me, okay? That's the thing here. Full disclosure, and I've done this on my channel before, I am not any kind of a certified, licensed electrical engineer or anything like that. My degrees are in computer software and programming, so you should verify anything like this that I ever tell you before you apply it to your own needs, okay? All I'm doing here is going to make the observation that if there's current flowing through this capacitor and it causes the electrolyte that is in here, whatever's left, to heat up, it could explode and cause a problem. And I don't want you to have any issues with that. So what I'm going to do is move this probe over to here, and I'm going to measure the current flowing from this power supply over through this meter, okay? I'm going to put it on, and I'm on milliamps. I'm not even on amps here, right? So I'm going to limit the amount of current that this thing can supply anyhow, so that even if this was a total short, we wouldn't have any real problems. And I'll prove that by just shorting out my power supply. This is current limited, and it has an electronic breaker in it. So it might even fire even all the way down there at 0. So we can see we have 130 milliamps at 0 volts. And if I crank this up, what'll happen is, all right, so the current is so limited that the electronic circuit breaker doesn't even kick in. But if I start allowing more current to flow, we'll start hearing a little click. That's a lot of amps. Well, this is actually rated to 3 amps. So when I get up to around 3 amps, it should say click off and say too much current. Right now, that's a lot of amps. I'm not going to do that. All right. Let's not tempt fate here. Point is, I can limit the current flow, and I can certainly supply a couple of amps if I want it. Okay. So voltage all the way down, current all the way down. Let's see what the fluke says about the voltage right now. Power supply all the way down as low as it'll go. I'm drawing 72 milliamps. The meter right now looks like a short, okay? Which is roughly what the meter here says. And as I said before, I trust this meter way more than that, and they don't disagree by enough to be significant at the moment, so this is okay, all right? So let's look then and see how much current is flowing through this capacitor. So what I'm going to do is I'm going to put the ground on the negative side, negative terminal. The bleeder resistor is off because the bleeder resistor is going to screw up my numbers and show some current flow. And I'll show you that in a minute. I'm going to put the plus supply on here. And now this is, plus is this, remember the meter looks like a short one. It's measuring current. So this is the positive probe when it comes to putting charge into this capacitor. Knobs all the way down, current limited as far as it can go, and I hook it up to this terminal here on our capacitor. I'm drawing, it shot up for a moment to 9 milliamps, and now we're back down here to 0. So what happened was, as the voltage, because this doesn't really go to 0, the voltage goes up a little bit. If I turn up the voltage here and bring it up to a few volts, as you can see, I'm at 0.5 volts now, and the current flowing from the power supply into this capacitor is measured on the meter. Now, I must have backed it off a little bit because it's flowing negative current. That means that the voltage in the power supply supplying is lower than the voltage in the capacitor, and it's actually flowing backwards into the power supply. So if I raise the voltage of the power supply up to like 5 volts, you can see we're drawing 50 milliamps here. Now that's because this current knob is so low. Let's turn it up and let us take some serious current here. Yeah, a teeny amount. And again, every time I raise the voltage, you'll see a current flow to charge the capacitor. And then as the voltage is stable, the capacitor, the current flowing through the capacitor is going down to almost nothing. So we're at we're so low, we're less than 1 milliamp, 0.4 milliamps. Okay, that's nothing. So we can go up here down to 5 volts. You can see the current charging the capacitor up, and then you see it drop back down once it is satisfied. As I move the probe around, I got a little noise in the reading here. Okay, this is how a capacitor is supposed to work. And it should draw no current, provided that the voltage coming out of this is stable. All right, so we're sub-milliamp here. In other words, this capacitor does not allow any DC leakage voltage that is of significantly measurable amount to flow through it continuously, and that's what would heat up this capacitor. Now, I'm going to put the bleeder on here. It's still all hooked up here. Watch what's going to happen to the current flow on on the fluke, and on this as well should shoot up. Because what I'm doing now is I'm actually measuring the current flowing through this resistor. All right? Now, the current flowing through the resistor right now is 25 milliamps, and this resistor is not even heating up. And this doesn't have any real volume or surface area to dissipate any heat. And the only way a resistor can drop the voltage as it goes through here is to dissipate it as heat. That's what these things do. So if this resistor can't even heat up enough for me to even sense with my finger that it's hot, this whole capacitor can't heat up with the same amount of current either, even if I was leaking 25 milliamps through here, which we know I'm not, because if I'm not bleeding off the charge or shunting current through here, I have less than 1 milliamp. So this thing here moves 100 times more current than this capacitor does when it's got a flat stable DC voltage. So this capacitor is acting very normally. I don't think it's going to blow up. I think it's working just fine. What I cannot measure using this, I can if we play around some more games with resistors and stuff, and we charge up the capacitor and watch how long it takes to charge through a resistor. We can calculate whether this capacitor really still has 95,000 microfarads or not. I don't really know. This meter here will also measure capacitance, but I'm not sure it'll measure it up that high. I put this back in voltage mode. Be very careful when you're switching your meter back and forth between volts and current. If this was still set to current mode right now and you put it on a capacitor that's charged, you can say bye-bye to your meter, unless your meter has a fuse or something, and this one does. It says fused. But don't measure voltage when your meter is in current mode. You're going to be really huge amount of trouble. Now I'm talking, so I need to double, super, triple check. The red probe over here is volts and ohms, and I'm on a voltage scale. And I want to make sure that this thing is discharged, right? So it's down to about 1 volt right now, and you can see it falling. So the bleeder here is doing its job. Let's turn this off so we don't have any problems with that. Yeah, all right. So I'm pretty happy with this. Let's take this resistor off of here. Well, let's make sure it's bled down. Now I'm only down to 1 volt, so I'm not that concerned. Let's go ahead and short it out so we're sure. Do not do this if you have more than half a volt or so in here, because that's a heck of a lot of current that you would get. All right. Let's now see what happens here. We should be really low. Yeah, okay, so 0.2 volts. All right, now what do? We put this on capacitor. I've never tried to put it on a capacitor this big before. I don't think it's going to work. It's not going to be accurate. You put this on like so. Now you hit this green button. It's measuring in microfarads. So it's going to be out of range. If it does work, it'll take a very long time to calculate it. Plus, I hooked it up backwards. Oops. I'm not sure it matters in here. This thing is really designed to measure some number of microfarads, not 95,000 microfarads. Yeah, that's not going to work. But just for fun, I thought I'd try. So here's one of the smaller ones. This is 12,000. Okay, it charges up. Well, I can keep the probe on there long enough for the thing to work. Again, this is a smaller capacitor, so it's going to charge up much faster and discharge much faster. But again, if I allow some current in there, we're at 1 volt. Let's bring it up to, say, 5 volts or something like that. And this is on the 12 volt rail, and this capacitor is rated at 40 volts. So this is working perfectly as well. No DC leakage current at all. I don't feel like this is going to be an unsafe situation. Let's go ahead and discharge this thing. Again, you don't want to just shunt these things with a screwdriver when there's 5 volts on it, because you could end up with a lot of sparking. And those tones are to let me know that the probes are not hooked up right for the setting that I've chosen. So I'm still got 1 volt on there. Let's wait for this thing to go down. There you go. Half a volt, 0.3, 0.2. There we go. It's going down now. Okay, and that's in the perfectly safe mode. One more cap. Let's make sure this one looks good. So again, all I'm going to get out of this is to know that the capacitors are not passing too much DC current flow. And the reason I don't want DC current flow, if that has been gone unstated, is because what I don't want is it to heat up. There's tons of current flow that goes in and out of there over the course of time when it's charging and discharging. But once it has become charged, you want it to stop. The current flow should stop, that is, and just sit there retaining its charge. So this is fine. It's drawing less current than anything else we looked at so far. Let's disconnect the power supply. Put this back on volts. Now, if it's got any leakage, it would discharge itself fairly quickly. And we left it at 5 volts. You still see the current, the voltage on the meter. Volts. If this is anywhere near 5 volts, which it is, it's not leaking any real current, okay? So that could probably sit there for a week like that if it wasn't being discharged somehow. So let's discharge it so I don't have a huge amount of, huge amount of charge sitting around on a cap on my bench. That would be really annoying. All right, so I think these capacitors are not unsafe. I don't know how much quality in terms of the capacitance they still have in them, right? There could be other degradations that these capacitors suffer from, but continuous current flow that will cause them to heat up and explode is not one of them. Now I have a toothbrush that I dedicate towards the task of removing flux from PC boards. And what I'm going to do is I'm going to hit this with some, what is this? I got this particular one is 91% isopropyl alcohol. Why? Because this is what was on sale last time I was at the store. I would assume just about any amount of alcohol would do. Don't waste your money on 99. You've got 70 or 90 or whatever will do fine. And you can just kind of go around, massage the gums, as they say, and it will, it's like paint thinner. It'll thin out the flux, and you don't want to let it evaporate, of course, because what'll happen is the flux will still be on your board. It'll just be spread out more evenly. So what I'm going to do is go ahead and clean up all these connectors like this. And then after I get most of it off, I mean, it's been this way for 45 years. I'm sure it would be okay if I ignored this completely. But then again, maybe not, because who knows? Maybe while I'm doing this, I'll find a broken trace or something in here because, it doesn't really work right. Of course, as I think about it, right, the front panel situation with the one LED, the data line that doesn't work, and the M1 line that doesn't work. If they were just LEDs that never lit up, that'd be one thing. But they're not. Well, the M1 never turns on, but the data line works sometimes, but not other times. When we look at the schematic of the CPU board in the front panel, we'll see that the data bus is that the ribbon cable, right, that goes directly to the front panel from the CPU board. So that has a special path for the data. But the M1 LED is lit up as a result of signals that come directly off this bus. So who knows? It may be that we have more than one problem with the system. Now, spoiler alert, if I think forward as to how the Z80, or rather the 8080 works, right? I spent most of my life with Z80s, but this system has an 8080 in it. And the 8080 has this status lines, including signals like M1, sharing the same pin on the CPU chip as the data lines, okay? It turns out that M1, the signal for M1 comes out the same pin of the CPU at different times as the data bit number 5, which is also not working right on our front panel. So from a 10,000 foot view, you might say these two problems are unrelated. I suspect, though, because of what I just told you, we'll have to fact check all that. But I believe that they'll turn out to be related. Now, I don't know. I mean, I don't have the whole schematic memorized. I've glanced at it before. I don't know if the D5 line and the M1 line are both fed through that ribbon cable, or if it gets one of them one way and the other way. I don't know. We'll get there soon enough. I'm going to dab dry this as I go a little bit because, like I said, I don't want this to evaporate and then leave all the flux still on the board, but, strewn out all over the place. You still have to eventually wipe all this off. All right, so I think this is a much better condition. And if I look around here, I don't know how well it picks up on the camera. I can see a number of individual pins here that have very cold-looking solder joints on them. I tip it around at different angles of light. Oh, geez, there's a massive blob of solder here. Huge, massive blob there as well. Yeah, look at the size of that thing there, and this one here. These are just nasty looking. All right, so maybe I'll go poke around a little bit with some heat. Yeah, here's another one right there that looks like, if any one of those happens to be related to the signals in question, even if they're not, this thing needs some help. All right, so the last bit of cleaning fun with this motherboard is going to be clean out the insides of these connectors. So for that, what I'm going to do, I'm going to try and get some alcohol right inside these connectors here. I'll dump it all over. Well, I'm going to show you what I'm going to do, and then I'm going to do this over the. Yeah, I'm going to have to do this over the laundry tub or something. But I got a new cleaner toothbrush, and I'm going to just fill this up with alcohol and just give it a little gentle scrub in there. I don't know how else to get in there. Really, these connectors are not really designed to be cleaned, as far as I can tell. So anyway, that's what I'm going to do. I'm going to hit all these, and then I'm going to call this done. All right, so we got some more interesting thing happening here. After I've gone and cleaned everything off, okay, I've removed some of the other cracking up grommets, and these holes somebody drilled out to make them bigger than these. I mean, some of them aren't even really round, and they're all messed up in the the coppers. I mean, jeez. Okay, great. They really wanted the grommets. I don't know what this particular model was came with. But what I'm done here is I've 3D printed, let me see, move this out of the way if you can see this. I don't know how well this works. I've 3D printed these little plastic things. What it really is essentially like two washers, a big washer that meets the head of the bolt like this, and then an inset one whose diameter of this inset one fits in these holes here. The bigger washer against the bolt wraps around the top of this thing, okay? So if I put this in like so, It's basically the same as a half of one of those grommets. So the bolt will sit down in there like this. There it goes. And the inset will hold it. So even if it slides around a little bit, nothing can touch the bolt itself, or the screw, won't touch the sides of the PC board, nor will the head. And I'll put a mate to the same thing on the underside of the board when I sit it back in the card cage. So the card cage is completely suspended on these 3D printed PETG inset thingies. Now, when I was giving an eyeball to those insets, I noticed this wire here, not good. It's basically completely falling off. I don't know if the coppers are lifted up here or not. This is really bad. So I'm going to have to pull that off. And I'm going to have to hope that I don't destroy the copper in the process here. So let's see what we got here. Oh, it doesn't feel good. Come on. Nah, it lifted up the copper. That's got to be the copper. Makes me wonder if this is part of why something doesn't work. You know, if we don't give it 12 volts, well, of course it would be much worse. Yeah, this whole trace, I don't know if I can get that on the camera. Let me see if I can get the focus right on this here. You can actually see it there. I mean, there's nothing you can do to fix this. I'm going to have to strip it back and then maybe put like a jumper wire in there to reconnect those traces. So what that means is, as it is, these two connectors probably never had whatever this voltage supply is, because this goes in here and goes both ways to these two connectors. That's why you see them on every other one, so it connects over like that. So yeah, this is the trace on the board there, sticking up. Nice. That could have been that way the whole time. What is this? This is the, okay, it says right here, plus 16. This thing doesn't connect to this. It goes to the one on the back of the board, which is minus. So this would have been for your minus 12 volt regulated line here. So none of the cards from here to the front panel had negative 12 volts. Nice. And I would have never known about that if I didn't try to clean all this stuff up. That would have been tough. Of course, if I probe around, I would have noticed, but still, come on, guys. Why does it not shock me, right? Okay, there we go. Let's start over. I'm scared to death to look at the other ones. So, what do I do, here or here? Might as well do this one. Why not? So, sure, this might be too big for the old scratch game. Scratch and win. So if we pull off some of the solder resist here, and then make a DIY pad. Surface mount wire connections. I mean, that's really all you got to do there. Okay. Now, let's tin this up. I almost always keep a piece of cardboard around, like a flap that I cut off in a DigiKey box for this very purpose. Now I'm melting the insulation. These would have been better if these were like Teflon wires, because Teflon usually it won't do that. Oh yeah, this is just like some kind of rubber coating, or get some like silicone insulation or something. All right. Looks like maybe I want to scratch a little more off of there. Okay. Let's tin this first. Oh yeah, that went on real good. Looking good. Now they're both tinned. I don't need any more solder. There's more than enough on there, I'm sure. Now, this is how all the IMSAI motherboards look like that I remembered seeing. They all had this extra set of wires going out here like this, but I thought they had bigger pads. Like, here's the 5s, right? Nice. This looks mostly cold on here too, doesn't it? I don't know. I'm gonna leave it. It's, well, geez, can't leave it well enough alone. If I mess this up though, we have a big mess on our hands. I just don't want the whole thing to come off, which it will if I play with it too much. Okay, that's at least a little better. It's on there. It's not going anywhere. Doesn't look beautiful, but okay. All right, so this at least has the wires back where they belong. Really make sure that's the right one. Yellow one's on the right that goes to the holes. Over here. That's the orange one. There's the yellow one, and it's on the one that goes below the board. Orange one is above. Orange one is above. Yellow one is below. Again, over there as well. Okay. Why, this thing looks like it's almost shorting out. But I don't want to push on it to get it away from this other track. Oh, jeez. It's been running this way for 40-some years. It's almost like, don't mess with it, but I gotta mess with it. Why? Oh, geez, that was barely even... Oh, God. Almost a cold solder joint in itself there. Let's clean this one up, too. You'd think they give you more clearance than these. I mean, it's not bad. I mean, it's certainly doable, but, geez. Does it have to be this risky? I gotta wait. You know, it's a miracle this thing ever worked. Oh, boy. All right, so now we have to put in some sort of a jumper here. Otherwise, it's never going to work. Now, I could use a lead on a component. Something a little bigger would be better. Use a piece of phone wire. Well, the problem here is as I heat this up, it's going to probably melt the other end. Don't want to mess with it too much. Cut off this extra. Grab the old magnifying glass. Make sure we look good. The part up in there doesn't look so good to me. Now, unless you're really sure, I usually grab one of these things. All right, this is a 30X. You got to get like really in there. You got to get your whole head right in there to see with this thing. Oops. But sometimes on the surface mount or a little teeny thing like this, you really want to know. So it looks good. So we've got our strip bare IMSAI 8080 card cage here. I have given this the alcohol bath, and the compressed air cleaning and the filth and muck is all gone here. That was a heck of an undertaking right there, okay? So I want to test this thing out. So what I'm going to do is I'm going to first put the power supply, back together again. 10-ton power supply. At least a 10-ton transformer. We have to solder all these wires back where they belong. And of course, once I reattach all the power lines, I can remount this up front. Yeah, that's what I'm going to do. That way, you know, because I don't want it to move around and hit something and short out. Grab the lead that goes to the front panel switch. That wire not on there. I'm doing this so I don't have to have live wiring on the front panel when I'm playing around. This is in there pretty good. It's not going to short out. I got live 110 here. Just don't reach in there. This is the low volt AC. The high volt AC is up underneath here. This down here is the, what is that? It's center tapped. plus and minus the 5-volt line, which is probably 8 volts AC, and then rectified and regulated down to 5 on the boards. These I'm gonna need to do something with. I've got a couple of crimp-ons. I'd rather do that and put more of these on those caps than just splice the wires back together in the sloppy way they used to be. If there's enough room on the terminals to do that, that's the goal here. Okay, so the plus and minus 12s, if memory serves, we're over here somewhere. The negative here is going to be ground, and then the plus here will be on the chassis ground for the other cap. And the minus on this one would be the negative 12 if I make this the negative 12 cap. So maybe that'll go like that. That looks okay. And the 5-volt, make sure we still have room for this thing. However, that was mounted maybe over here. These look like, yeah, it looks like it would mount quite nicely right there. Alrighty, these are all mounted in there. Well, these used to run through there. That's good. Let me put the big boy on here. Alrighty. Okay, these are all back in and hunky-dory. I'm going to go ahead and put some of these crimp-ons on these wires, but these are kind of skinny. So what I'm going to do is I'm going to tin them with some solder before I crimp them on, so that when I crimp them, it's got something to bite into more than just a little wire. Now these colors here should also match the ones on the main motherboard, which is also labeled. So, sanity check. Orange comes to the outer rail, which says plus 16, which means the yellow must be minus on the bottom. Yes. Does that jive with this? Yes, it does. This is plus, and that says minus over there. So, again, I'm still going to measure it, but I like to look at all this circumstantial evidence over and over and over again. At times like this, just to kind of double confirm. It would be nice if I had different colored ones of these, but I don't. I only have one. There might for bigger wire, a little bit bigger wire here. But I think they'll crimp down just fine. All right, so we put the wire in there. The proper depth, and then give it a... Yeah, these are meant for much bigger wires. Actually, I think I just did it backwards. Nice shooting, Tex. I think I ruined this one. Well, let's take 2. Crimp on this one. There we go. That's definitely in there. There's the notch. Yeah, this really wants a little bit bigger wire in there, but it's in there. Okay. Now, this particular power supply can provide, tens of amps, and I'm going to tighten up that one terminal for now. Just get it snug so that the wire doesn't pop off and hit something stupid. All right, yeah, so all the grounds are going to go. Okay, so they're not going to float around and hit anything. Then I got this clipper here. And clip this bad boy onto there. Favorite flute meter here. Place where we can actually read it. There we go. I love the lighting problem here. There we go. That looks okay. Now I got a ground fault and a special breaker just for my bench, so if anything bad happens, it should be localized. All right. Well, that's a good sign. So this should be my 5-volt, unfiltered. This should be my negative, I think. Negative 11. Boy, I would expect a lot more than negative 11 on there. Positive 11. That is really a little weak for a 12-volt and minus 12-volt bus that's supposed to be really 16. Now this is DC, so that might actually be measuring the RMS value. I put my meter now onto the AC range. It's interesting. So yeah, if we put a scope on here, we're going to see a lot of ripple. So these are full wave bridge, right? This is a center tap AC transformer with a ground in the middle tap, right? So the two big giant transistors in here, or two big giant diodes, I meant to say, are going to be a full wave rectifier for the 5 volts, okay? Now, let's move this over a little bit. Let's go back to this. Let's put the capacitors on now. And do this again. I don't know how the lighting is so terrible. I apologize. Fine, there you go. There's a place we can put the meter that we can all see it. Yay. All right. Now, no volts at all. There's no capacitors on there to hold on to anything. Okay, here we go. Now, if we just hook this up to the 5 volts on this cap, all right, there's a bleeder resistor over here. So I don't have to worry about getting rid of the charge since this is otherwise unloaded. All right, so let me go ahead and tighten this up. And we saw that was like 6 point whatever volts unloaded, right? When we look at it with the capacitor, this will charge up to the peak voltage, and then when there's a current drain, it'll droop down until the next time there's a peak. So this actually should go up by about almost 40% more voltage, give or take. So let's see how high it goes with the cap on here. Now I'm going to stand back in case somebody did something dumb, like didn't notice that this is plus and minus, right? This is a big plus, okay? And when I do stuff like this when I'm talking, I have to really kind of double check. So sorry about that. All right, so that's 9 volts it charged up to. And you can see how long it's going to take to go back down now. So that's the bleeder resistor draining it off, okay? Now I'm not going to short this out myself. We'll wait for that to go down before we poke around. Now, you can still touch it. It's not going to be a problem at 7 volts. It's just if you shorted this thing out with metal, you could get 20 amps or something like that off of this thing. It's good enough for some serious arc welding. So this tells me that the power supply here is fine. And I hooked up the capacitors right. And this should be okay. What I'd like to do is go back to my test the other day and sit it out in the garage and let it run for an hour just to make sure, once again, that these old capacitors aren't going to blow up while I'm working in the general vicinity. If you've ever seen one of these blow up, they can be quite catastrophic. Just do a Google search on electrolytic capacitor explosion on YouTube. There'll be all kinds of videos of people blowing them up on purpose, just so you can see what they can do. It's not a pleasant thing to happen when you're in the same room. All right, so this is the bottom of the motherboard, and I got the old glue gun going here, and the grommets, as I mentioned, are all dried out, and most of them cracked and fell out. The rest I just knocked out as I was going along. So what I got here is a 3D printed. It's basically a washer with kind of a nose that sticks out to one side that sets down in this hole so that it's sticking through the PC board but not out the other side. All right. Now this thing will mate with another one on the other side, face to face, trap the circuit board in the middle, just like the grommet did. But this is a 2-piece design. Now, in order to get this thing in the card cage without having the thing fall out, what I'm going to do is I'm going to hit each one of these with a tiny little dab of hot glue so that when I flip the board over, they don't all fall out. And one little teeny dab, and of course, it's all over the place. And this, of course, is why, if you've ever watched the EEV blog guy, he calls this stuff hot snot. And, you know, that's not a bad name for it. It's just gooey stuff all over the place. All right, so another little teeny dab. And that's all you need. It's just to hold them in long enough to flip the circuit board upside down and not have them all fall out. All right, so there you go. These are all on there, and they stay on there. That's good. Let's see if we can put this back in the card cage. Which is back to its full playing weight here, I can see. Oh, come on. Oh, this is probably better to go this way. If you're going to mess with one of these, there's a front and a back to this card. The motherboard, because the front one here needs to stick out in front of here. This is where the front panel goes. Now, if there was a connector back here, it could probably be flipped around and go in either way, but that's not the case with this one. Well, let's get all these wires tucked. Okay, these are nice and long. These all reach there. The white ones all reach. That's a good sign. They can all reach to where they gotta go. Just barely on this one. Well, that's all good. All right. Not bad. Okay. Now, I also have some same thing for the top. Made together like that kind of thing. So that way the screw, I'll still use the lovely wood screws. I don't have anything else. And there's no PEMs in there anyway, so it's got to be something self-tapping. And, well, that was good enough for 40 years. 45 years at this point. Now, when I reseat a screw like this, what I do is I turn it backwards until I feel it. You could maybe even Mike pick that one up until you feel it fall into the original threads that it cut from before. This is aluminum. You don't want these to cut new threads more than once. Nuh-uh, only once. Because once you grind out all the aluminum, you got nothing. So that screw is in. The board seems reasonable. All right, let's put a couple more of these in just to get it just enough to run the front panel. The board's in there. Well, I'm going to put another one over here somewhere. Because the thing is, when you put a board in an S100 slot, there's a lot of friction in there. When you pull on it, I don't want the thing to come up. That's probably a bad idea. And if you're messing around with these, you're not putting lug nuts on a wheel here, all right? These aren't car wheels. Just enough to hold this thing in. It's not really going to go anywhere. There's nothing really around pushing it around. When you pull a card out, you are pulling up on it, but that's not going to be a major problem. As long as the screws bite in any way, shape, or form, they'll hold the thing in. None of it's really going to go anywhere. We put a zip tie if we want to, but... All right, so the number one thing we need to do now is make sure nothing is shorted out. All the whites are together, all the blacks and blacks are together, all the oranges, all the yellows are together, okay? Good on this side. Over here, we need to make sure that the orange is always connected to the same bus, which is the top side bus here, and I can see that's the case. The yellows all connect to the track that goes to the backside bus, and I can see that's the case there. The whites both go here. The blacks are both the ground. Maybe I should put another bolt back there, but I'm going to risk it. And these all look like they're going to be okay. You're going to have to be careful when you put the circuit boards in here so that you don't try to, put one in there and get it hung up on the wire, but that's usually not a problem. Anybody who's capable of inserting a board should check that out. No, I'm not going to put the motherboard or the front panel in there, what IMSAI calls the CPA. I want to just fire this thing up, check all the voltages again, make sure everything's fine. And you know what I'm going to do? I'm going to turn this around so that if it decides to do anything strange, it doesn't do it in my face. It'll do it over there. 1 foot of distance, that's enough room, right? These things will shoot straight up is what they'll do if they decide to vent, because that's where the vents are, okay? And I'm sure it's not, because I've been running for the last hour, once again, out in ye olde garage. Home on the DC range. Okay, let's see. Let's do a resistance check and put this on ohms and check between the chassis and the ground. And I've got infinite ohms. That's a good sign, because I didn't expect the negative voltage to be connected to chassis ground. For that matter, it shouldn't really be connected to anything else either. Short it to itself. Make sure the meter's hooked up right. Yes. Is it here? No. Here? No. Ground over here? No. Okay. Nothing, nothing, nothing. All right. DC volts. This is the main 5-volt bus right here. All right. Let's see what's going on. Now, once again, if I tap the power ever so briefly, it'll charge those capacitors up and leave them charged for quite a while. 9 volts, 12 volts and falling, negative and falling. So that is a good sign. All right, so this whole thing should be able to just put cards in there and run it again at this point. Now, I took the liberty of wiping down this edge connector here on the front panel. That's really the only thing that hooks it up to anything. Actually, we need to be careful, because there could still be some power on those caps. Let's not plug it in while it's still got something happening there. With nothing on there but the bleeder resistors, this could take a few minutes to discharge. Once we hook up the board, it'll go down much faster. So we're still looking at 2.8 volts on there. I don't know how well this is easy to see this. Right? There we go. It's 2.5 volts. Now I plug in the board, it'll drain it right away, but let's give it a little time before we get too creative. All right, so I've done nothing other than clean this. I didn't redo any solder joints or anything. And this is actually very messy right here. I didn't notice how bad that really is. There's some kludgy wires in here, which are probably part of the assembly guide. I should look to see if I got a manual for the specific revision of this board here. All right, so the voltage is down. Let's go ahead and plug in this thing here. Now, I don't actually have to put the CPU in. This will probably come online and light up without the CPU. But without any of the standoffs, if I push it back, I'm shorting this thing out. And the bolts that hold this in go through a lot of stuff. And what I want to be able to do is put probes in from the front if there's a problem. I'm hoping that just the fact that we cleaned it up will take care of our problems here. Now, it seems to me that what we really need to do here is just make sure that it doesn't short out against the panel here. Oops. Well, this is going to be fun putting this all back together. So what we could do is just put the hand tight some of the screws in a little bit with the spacers in here. It can come forward, but it won't let it go back, and that's the key. Okay, so what I'm going to do is I'll put in a couple of these in here like this, just to hold it. Make sure we're good here. Make sure the board's seated. Luckily, the screw still lines up with our clowning around with the the spacing on the motherboard. If we lifted it up, any of these bolts may not align anymore, so I'm glad to see those still go in. Now, I'm not going to play games with the 110 volt power over here. I'm going to leave it the way it is so that I don't have, high voltage on the front panel. I don't really know how well the front panel works without the CPU. CPU generates a lot of signals that this thing uses, and this generates a lot of signals that go back. And maybe I should put the CPU in there. I'm going to put it right here. Doesn't really matter where it goes as long as the ribbon cable reaches and connects okay. And this is all gold plated, and the socket in here is all gold plated. And it doesn't look like it's covered with glue or anything like that. So this should all be fine. Never had a more satisfying clunk inserting it. All right, let's just turn it on. There's no memory, so it'll run, but it'll get all FFs, which I think is restart 38. If we actually run any code. Is it safe? All right, let's see what happens here. The only thing that could go wrong at this point would be if I have the voltages backwards, like the plus and minus 12. But I checked it on the printed side of the circuit card here that said that it's positive on this edge, and that's what I read. So I'm so nervous. If I blow these up, I'm never going to buy another one. Fortunately, I have a whole second IMSAI 8080. I'll just hide this if I destroy it. And I'll delete these videos. No one will ever know. We don't need that. Okay, orange is plus. Okay, here we go. No explosions, please. There, we got some LEDs on, and I can't remember which switch does what. I think this is the reset. Actually, that's the run. This one's reset. And when I reset it, the LEDs are doing the same thing it always did before. And the M1 and the data bit number 5 are failing here. So we're no better off than we were before. But you know what? We're no worse off either. Let me see if I can get this thing to reset itself. Come on, reset, reset. How do I do this? Can't get it to stop. There we go. It finally stopped. And this is the reset. Oops, that's the run, dummy. There we go. Got it to stop again. This is the reset. Boy, I don't know. The examine and the examine next are going, and so on. So I have a theory. I have a theory based on the fact that the M1 signal and the D5 signal, both of which are weird, are related on the 8080 due to the way the chip pins are multiplexed. So next time, what we'll do is we'll get out the schematics and look and see how the front panel works, how the CPU works, how they work together, and start probing around on some of these chips to figure out which signals are working and not working, which ones look right. So thanks for watching. I'll see you next time.